me, okay, why are we doing this in C? And this is an assembler class. The fact of the matter is, you will probably never use assembler, but you will use C to say, like, you're running Python and you need something really fast. You'll use C. The same with Go or Rust. They all have C as an API. So you can actually weave together your code base through many different languages and then calling C subroutines that have been vetted for the past 15 years. Okay. Like the C++ boost libraries. I'll put that in the terminal just so you can see what it is. It's actually called Boost. It's a C++ library, and it speeds up your code dramatically. It's one of the most peer-reviewed, vetted, tested chunks of code you can find. So if you want to use the Boost libraries in your C++ code, you can bet they're pretty bug-free. Okay. Help make networking fast, caching fast, all that good stuff. Okay. All right. So you could start by typing all this fun stuff in. And there's a couple ways we can do that. This is important enough to type in. And you can use the Jeremy Lab if you want, and use the Jupyter Notebook, or you can use the command line and use VI. I don't really care. But the reason I want you to type this in, because there's something happens when you type things in or when you write it down with your pencil and paper. I don't know about you, but I go shopping every now and then for various groceries. If I try to remember it in my head, I always come home with something I've missed. Oh, darn, I forgot this. Oh, darn, I forgot that. But if I write the list and then go to the store, I almost never have to read the list, and I get everything on the list. Why is that? Well, there's plenty of neuroscience that says when you use your hand and you write something out longhand, you're creating a much stronger connection in your long-term memory. It's called synthesis. You actually, like if you wrote this out once longhand, you're going to remember it much better than if you typed it in. And I've got all kinds of neuroscience proof of that, but you probably know it yourself anyway, okay? Because you can type really fast and take a bunch of notes. Some of you can actually probably type as fast as I'm speaking. And I'll test you tomorrow, and you'll do just as well as the person who did handwriting. 6 weeks from now, you won't remember a thing, but the person who did the handwriting is going to remember much more than you did. So there's something to it, okay? Just something for your, it's a great way to prep for interviewing. And I showed this in my Linux class. This is a very serious book with some very complex problems that make your brain melt. But they give you examples of what interview questions are at Google, Facebook, Amazon, Microsoft. Then the person who put this together is a software engineer, and she got brought in to start doing HR and interviews. So she started creating interview questions, and now she's got this consulting practice, writing books and teaching people how to pass interviews. Because some people are really good at programming, but they're lousy at interviewing. Other people are great at interviewing, the great honeymoon experience, but they suck as programmers, okay? So how do you find the difference? Well, this is a great book, okay? Bring that just for your edification. It's called Cracking the Coding Interview. And you can find it anywhere. All right. So go ahead and type this in, and it shouldn't take you too long because you can use the Jeremy lab. Now, some of you that are clever, you can do a screenshot, run it through an OCR and get the text. I've had students do that in the past. Extra points. Show me how you did it. Okay. And let's see. This one. So I have it as a PDF. It's not in my public file. So I'll put it back up on the screen. Now there's arguments to, for, and against making you type stuff in. I personally like the idea of working at the command line and having you learn how to navigate the command line. I was working with a Python student today and new to computing in general, and was asking questions like, why do we have a different prompt between this and why do we need a different prompt? What's the difference? I know. Thought I might approach this. So when I do Python 3 and hit enter, what am I looking at? Give me a guess. Doesn't matter if you're wrong. Nobody's brave enough. Okay, let me do this again. All right. I did that with Python. I'm going to open another window here. And I'm going to type in Lua. What do I get? I do that again, and I type in bash. What do I get? Type in Perl. Nothing. Let's see, what else do I have installed? No, Go won't work that way. New list. That might be installed. What about that? No guesses, no ganders. When we type in Lua and hit enter, what's happening is that we fire up the Lua interpreter that runs the Lua code from the command line. So I can now type in any legitimate Lua syntax and have it work. Okay, I'll exit out of this one. So when I type in Python and get the triple chevron, same principle applies. I can type in legitimate Python code and have it work. Okay, so if I want to exit, I have to do it that way. But when I type in bash, you notice the prompt didn't change. But bash is the same thing. I can type in legitimate bash commands and have them work. Okay. This command line thing does not go away with cloud computing. It gets even more gnarly. For example, VISH, VIRSH. This is the commands that you can use for the virtual manager to manage all your virtual machines. You can do the same thing with LVM, same thing with printing. On and on the story goes. So it's one of those things, you're not exposed to this. So you don't even know this exists. But this is how it all works. Right? Kind of like the spark plug idea. Okay. So let me bring that code back up so you can look at it. I'll get off my high horse here. All right. Go ahead and type it in. Now, as we go through this, we will compile this a few times and we'll go through it. We'll make some errors and we'll fix it. So follow along, take notes. But I can tell you that the foo and the foo.h don't exist yet. So we will have to go through and make that stuff work. Okay. And I'll shut up, at least for a few minutes. Done yet? Okay. So if you're using the Jupyter notebook, you can log in and go to your directories, ASM, and type it in there. Same thing, it just looks different. Those are two square brackets. Might be a little hard to see, but those are square brackets. Which is easier to see, the white or the dark? The dark one? Okay. And of course, as we go through this, we'll put it in the debugger. And while you're copying this code and getting it in, I'm going to take the same code and put it on the Raspberry, which is over here, and I'll just move it out of the window so it won't be in the way. Everybody got it? We're getting there? Okay. All right. Let's try to compile it just as it is. We're going to talk about the errors that you see. Ideas. Will it compile? Probably not, because foo dot something doesn't exist, does it? So let's see what happens. So I will take this argument list, all right, right there, and I will copy that, save it, hit clear, and then just paste it. And notice it says, wait a minute, undefined reference to foo, collect to error, LD returned 1 exit status, returned 1 exit status. In other words, abort, I quit, I ain't gonna do it. And notice the temp /tmp ccqjx. That's an actual file that's in your temp directory that will be deleted in time. Stuff in your user temp and temp directory will be purged over time. Windows does the same thing. It's just done in the background, okay? So let's fix the code to make it work, okay? So I will comment that out and comment out this. So the only two lines that return to foo is the foo.h and the foo subroutine function. Recompile. Now I can run it. Args lab 5. Remember last week what we did? Ancient history. We said we want two integers when I put in nothing. What happened when we didn't do that? We got a core dump, right? How many remember that? All right, a couple of you do. I mean, some of you are tracking. So if I do 7, 7, it's, look, your sum is 14. Yippee skippy. So it's working. But now I need to create foo and foo.h, foo c and foo h. Yes?
Go back and show us what you took out. Bit too fast for us to see.
You're going to have to yell louder.
Could you go back and show us what you took out? For the
Oh, those two lines? The only two lines that had foo in it. That's it. That was the one at the top. I had the include and the one down at the bottom that was calling it. Now, the way we are going to create our headers is what we would call assembly language friendly. Okay. There are other ways, but we are going to do this according to the textbooks, that when we bring it up in the debugger, we have memory bounds. Okay, that way we'll kind of know where our stuff is. It'll be all over the map. Okay. So basically, what will happen with foo is that we pass this value A, which is what? The sum of our two fields that we put on the command line, right? And then it displays the sum. Then A will be sent to foo, and it will return with an additional 8. So we're basically adding 8 to A by way of a function call. If you don't understand functions and how they work, tune in. The way functions work is that when you pass a value, the function itself gets called. The results of the function are in the name of the function. So when I pass, let's say this is 10, 5 and 5 is 10. I pass 10 to the function, it adds 8. Where is the value 18 stored when it comes back and the printf prints it? In the name called foo. So we call, we send it our value, and it returns the +8. So when we call foo, the value is where? In the name of the function. And that's pretty much how it works in all programming languages. You do have pass by value and pass by reference, but I'll leave that for another programming class. Let's get you through this. So now what we have to do is we need to create our foo.h and our foo.c. Okay. So I will go ahead and let's go ahead and exit this. And this is what foo.h looks like. Now, this is a typical .h file. Now, the textbook goes into long detail explaining this. Technically, this is not needed, but for the sake of what we're doing in this class, we want it because we want to see how all this stuff weaves together. Because when you bring this up in the debugger, Now you have a main that's calling a function that's calling a header. Where are you? So, and notice how it's upcased and it has a trailing underscore. Long esoteric discussions go there, which I will leave out. Just blame it on not enough memory when you had early days of computing. You can blame a lot of the weirdness on having a 4K computer. Now that when it says include card, that's a memory card. So it actually creates some type checking. So if somebody tries to do stack smashing on your code, they won't be able to smash it because it will stay in its little box. And stack smashing is an exploit technique that works rather well. Yeah.
Do you want us to make this on both the res and
Yeah. Yeah. So do this on both the Raspberry and the Jeremy box in your assembler directory, ASM. And notice how it says init Z. I need to explain that as we move through this. So much of what we do in our world, it just works. And we don't know why. But if it just stops working, we get kind of upset. I had a very, let me bring up the other piece of code here for you. Make sure I'm on the right machine. And this is the foo.c. Right there. Okay. Now the way this works, we technically don't need the foo.h here. It's because foo.h and foo.c are bound together by this. Skip that. But I have a 2022 Honda Ridgeline that would not pass smog. And I was doing all this wonderful information, reading about it, and come to find out it had a recall. It needed a software update in order to pass smog. So I took my car into the dealer and they charge you like 160 bucks just to plug in the little device. And they flashed my EEPROM and it worked. So I take it to the smog shop. It still didn't pass smog. And then I call the 1-800 Honda Help Me phone line. I said, hey, this update's in and it didn't pass smog. And they said, how long have you driven it? Oh, about 50 miles. Well, you need about 1,000 miles before you get it re-smogged. And I'm like, why? Oh, the logic in the smog computer will optimize smog based on your driving habits. Isn't that interesting? You use your Google browser and it knows who you are based on your mouse clicks. Now your car knows how you drive and you can get discounts on your car insurance if you plug in this little thingy and it basically monitors your driving in real time. No, thank you. So once we get these keyed in, and they're in the same directory as your args, okay? Notice I have an X, I have an X, I have a Z. It does not matter. Now this is off the Raspberry Pi, so I'll just bring down this the smaller part. The code is the same between the two. The compile lines are slightly different. So I'll do that. And that. Notice it says it's A here. Remember in Python, anybody, that when you call a function, it's positionally dependent. You can have ABC, pass it to a function. Doesn't matter. It can be XYZ as long as there's 3. And they're the same type. We're all ints in this case. Doesn't matter what you call it. You can call it W here, Q there, A there. Or you can call it all the same, and they get really confused in the debugger. You got it? Ready to compile?
I'm having a hard time getting to get the code correct. Before we add Boolean, I'm having a hard time getting the parts.
Just put it in the same direction. I'm sure. The code is correct. Well, of course, you're not. Yeah.
You're running to go.
Okay, that'd be weird. That should go on.
Yeah, when I edited it.
Why does that? Well, fix it. Let's compile it again. Look here. Let's see what it's telling you. It says, what's the first error? It says, input string. You mean F?
Well, you need to
Yes, you meant print F. There is no print in C. There is in Python.
So
It's not print F. Pardon? Yep, that's exactly what we're getting. We'll be getting on the RAS 5, the GS tab -G. So the compile line. Yeah. Yep. All right, you guys are good. Zooming ahead, good. All right. And it's, anyway. So let's compile this now. I'll take a look at my code. Let's take this one off that's the Raspberry. And I'll move this over here. Move this over. All right. Now, if I look at my args lab 5, I have now created my foo and my foo.c. Notice there's no .c at the end of this foo here. It's implied. I'll show you how that works in a second here. So if I take my compile line that I just did, maybe not. Let's see if it's in my cut buffer somewhere. Yep, there it is. There's my compile line. And notice I get this error again. Darn it. Well, I created my foo and my, there it is, foo C and foo H. Why didn't it work?
I don't think we compiled it.
I didn't technically, because I need to put foo.c on the same line as argc. Right here, I need foo.c to tell the compiler I want this other piece of C source code to be linked in with my main and then put into the object code of my runtime of args lab 5. So I need the C there. And now when I hit enter, there's no errors. Now when I run the command, args lab 5, I'll say 5 and 9. How about 5 and, I don't know, 23. There we go. Notice what it did. So it called my foo. Now, let's get everybody this far. Okay. Try to get this to work on both machines. On the Raspberry, you will find that you will get an error. Okay. Let's see here. Let's do up arrow. There we go. On the Raspberry, if I use the same command line, that's not the Raspberry. Okay, let me close that window. There's the Raspberry. If I use the same command line, which is, oops, that's, I can't do that. Put that. So this is the command line that we would use if we copied it, right? It's just GS tabs. Oops. So the Raspberry, using the same compile line, I get an error. That's because the compiler behaves differently because it's a different architecture. So I can basically still get my debugging symbols by using -G. And I get my compile. And I've got my foo.c. So now I can do args lab 5, 6 and 7. It adds 13 and 8 and 21. So what have we done? We've created our main, which basically is our args 5 lab 5 thing. And we created a function call that happens to live in an external file called foo.c. And then we declared a header for our foo.c. So when it gets linked in, it's all part of the same object. And this works the same on both the Raspberry and the Intel, or ARM and Intel, Raspberry and Ubuntu, basically Linux. Okay, working the same. Now, how many are here? I've got this work. Okay, 3 or 4 of you. Okay, let's get everybody up to this point. And then here's your future assignment. I'm going to give you demo code of Fibonacci sequence and demo code of a factorial. And you will do the same thing you did with foo with Fibonacci.
Oh, you're gonna space.
Where's your food?
Shit like that, right? Yeah.
What did I see you need to ask for spam? Get up our that's how you get it to link. You need the foo.c with the args.
Seems like this is pretty rad actually. I don't know.
Oh, you spelled funded. It's not, you spelled infinity.
Oh.
Infinity.
Oh.
Yeah. It should just be,
Started working on the service today.
if def.
Apparently.
Good,
But I actually got one.
good. We're all not quite. We're troubleshooting typos.
Yeah, next week,
Fun.
like install SSDs and everyone. So we can start
I gotta do that one.
Oh, why? What I pretty shit? Why? Do you have a hard drive?
Dude, yeah, I got a hard drive and like 200 gigabytes of it.
Why do you have a rebuild?
Yeah.
Yeah, that'll do it. 'Cause that's what I had for a long time. And then I remember I was like, fucking, I think I got an SSD because I didn't know what an SSD was. And I got like a 2 terabyte hard drive. Just small, so like we were trying to do like 2 minutes. And I was like, why is this happening? I thought it was like a virus.
Yeah.
And I was like super into computers.
Like everything I've seen online, it's like when I was like first learning about it, like the first thing, you don't really need them, but like once you start using them, you're never gonna want it.
Yeah, because like I have a 4 terabyte hard drive that I used to keep like game clip, and it's so slow. Dude, it's pretty cheap now. It's like $700.
So once you get everything keyed in, your compile line will need foo.c in addition to GCC. Okay, so you need those. That's what's in C. It doesn't look like the H. You can't, the C is different. Okay, this is a legitimate C code. Okay.
I bought an SSD plan. I should have used that website if I see cable. And I was wondering like plug it in, just like if I had my hard drive. Now in terms of like no PC before you buy it. Yeah.
Dude, I got a friend who's like,
No, ever since then though, I always do that, especially with computer stuff.
yeah, especially because I don't know, the way that stuff works. It's like there's no downtime, right? And the GPU is like that.
Dude, I bought a video and it's tried like 2 weeks after I got it. So I was trying to take that one. I think it was last Tuesday because I had like an hour to then it kept saying big failed, like people was crashing. It was wrong. And I felt like, oh, I was like, why was it when yours corrected or something like that? And then my friend was like, yeah, do this brand check. And then, yeah, like brand just like not even functional. Yes. Yeah, I gotta read it. I used to have this exact same mistakes, but that was
Was it not your fault? Or like the new ones were?
just cheap Chinese brand.
That's a
People like the thing is everyone who plays so much like all this rock coach like single player.
All right.
There was a kid.
I'm assuming we're getting closer to success and getting this working. Now, we have this command line that has basically 2 C files on it, right? There's just 2 of them. Has anybody compiled anything of significance off the internet? Like from GitHub? Let me show you the joys of what actually happens when you do this. On the Raspberry, I'm going to do this. I want to show you. So just watch what I'm doing here. And I'm going to explain how this monster behaves in this. And what do I have? I don't have anything. Darn, that wouldn't work. That wouldn't work. There it is. I have the Python source code for Python 11. Now on the Raspberry Pi, what I'm going to do is extract that. First of all, let's see how big it is. I'm teaching you this because compiling from source, you're gonna have to know how to do. That you're gonna have to do that, okay? So it's about, what is that, 98 megabyte. So I'm going to untar this. Tar stands for tape archive, and I do tar xdf, and then type in Python, change directory Python, and look in here. Oh, look at all this cool stuff. And let's see here. Does it have? Got the make file pre. I can do this. Configure. And look what it's doing. This ./configure came with my bundled things. What it's doing is it's going through all of my libraries on my Raspberry Pi to verify I can actually compile the source code of Python 3.11 on the Raspberry. So when you actually compile from source, there's a lot of pieces you have to put in place to make everything work right, okay? All right, if you want to release build with stable, do that. Yes, I think I want to do that because why not? Let's make it stable, and let's make it PIMIZ. Now goes through the whole thing again. And this configure is doing something very clever. The code for this has been around for decades. It will break your brain if you try to figure it out, okay? Notice the very last thing it did. Creating makefile. This is where we're going next. We have a compile line that has 2 C source codes in it. Big deal. Well, how many C source codes do I actually have here? Let's find out. Find, and let's go with -name, anything that ends with C. Wow, that's a lot of them. That's just C. Now let's do word count minus L. 326. Anybody want to type in 326? No. So what's in this thing called a makefile? That's what's in there. This makefile does all kinds of lovely things for you that you do not have to now type in. Jeremy, on the back wall there, the reason we have the lab, would do this all the time for the machines at Zynga to optimize the kernel for the maximum speed and throughput. And I'm still scrolling. I got a ways to go to get to the top of this. So knowing what a makefile is where we're going next. And it is covered in your book. Okay. I haven't assigned it. And this much I can bet. Most of you are fairly young. So you don't do something unless there's a reward at the end of it, like a grade. Well, I don't come from that place anymore. I come from industry. Just because there's not a reward doesn't mean you need to go, doesn't mean you don't need to learn it. Go learn your own stuff. Okay. Because that's what's going to happen in industry. They're just going to throw it at you and you go, oh dear, what do I do now? All right. So I have this monstrous make file that goes on and on and on. Okay. Now, there is a tool that we use called make. And this make, there's lots of different flavors of it. They have, anyway, this is how it works. When I say, I type in the word make, what this does is it, in your current working directory, it looks for the file called, I'll just do head, so I get the top 10 lines, make file, okay? Make calls make file, and the convention is uppercase M, make file. That's where you modify your make file to do what you want it to do. Okay. So I can type in make now all by itself. And guess what? It's now compiling my Python source code for 3.11 on the Raspberry. So this is probably making my, if I was to bring up a temperature sensor on the CPU, it would probably start climbing. Because doing these types of compiles can take some horsepower, okay? And it will probably take a while. We are going to write a make file, and I'm going to show you how to do it. Okay. And what we'll do is we're going to use this information in our make file. Okay. There are some caveats with the make file, and I will explain them. Now, in the back on the Raspberry Pi online, and you can find Mr. Plantz's earlier books online for free. There's a section in the back that talks about makefile. Okay. There's also a gazillion tutorials. Okay. Been around a long time. This is what it looks like. I'm going to use VI to show you the caveats. What did I call it? Make uses a file called makefile in the same directory where all my stuff is, okay? And it looks basically like this. If I type in make all, it will say, let's see, I want it to call argz lab 5. This is what it's going to create. That's my -O, okay? And then I need to call it argz lab 5 colon argz lab Then I need to create. Let's start with this. You see how I did the tab key? I want you to notice something about that tab key. And what I'm going to do is I'm going to abbreviate this a little bit. And I'm going to leave out the foo part and change my source code so I can get you an idea of what this is going to do. Oh, and then there's one down here at the end called clean. RM hello dot. Notice I'm getting that funny red stuff. Okay. My Python or my VI script converts tabs into spaces. Make will not work with spaces. You must use tabs. So how do I put a tab in here? You go like this. Escape, Control V, tab key. See if that works. Let me turn that off. Oh, I've got something else going on here. I've got a mark going. Let me save it. Nope. Clean. There. Hello. Oh. Okay. Let's see if it actually behaves. I might have to rename my Vim file. Oh, there it is. I'm using a Vim command that allows me to turn on and turn off white space. And you see that vertical bar I? Anybody remember their ASCII? The ASCII chart? This is a tab key. Okay. So I need to put another one here. Escape. Control V, tab. Why didn't you do it? Okay. Oh, it needs to be in the insert mode. Never mind. Insert. Control V, tab. There we go. Undo. Insert. Control V, tab. All right. Now hit F2, turn those on and off. You can see the tabs are being expanded. Say what? Oh, I'm using F2. It's part of my Vim script. If you're in VI, I'll show you how to do that in VI, but since this isn't really a VI class, I just need to stress tabs have to be in your make file. You can use this. That'll put a tab in for you. This is your editor that's in right here. It's just there. Okay. This is the editor that's in the Jupyter notebook. Okay. Do the same thing. Okay. Doesn't need to be hello, it needs to be args, sorry. I'm copying from another makefile. Sorry about that. Talking and typing is not always comes back to haunt me. Now let's talk about what this does. Okay. When I say make space all, which is the default, it will create an executable called args5. Okay. Args lab 5. If I say make space args underscore lab 5, it only creates the object. Okay. Creates the object code. That needs to be a .c here. That one. All. So basically this is redundant. This one is kind of redundant, but that's okay. This one, if I say make args underscore lab5.0, it only compiles the C source code into the object. It will not create an executable. If I say make space clean, it removes the objects. Okay. So let's see how this thing works. But first of all, I have to fix my argc thing, because I left foo out, right? We're creating a very simple makefile. We're going to see if it works. Make all. Nuts. What did I do? GCC O labs. Whoops, long file. Make all, did that one. And I'll put there. Lab. See, let's see how this works. Let's try make clean. Okay, that means it's not out there. Make args lab 5.0. It says it's up to date. So why didn't it delete it? Make clean args lab 2. It should have deleted that file. Why didn't it? What's my typo?
Should it be lab 5 and not labs 5?
Oh, labs 5. Labs 5. Args. Oh, yeah, duh. Good point. So much easier when other people see your typos. You know, when you get a job, it's really handy just to stand over your mentor and watch how they code, because you can learn a lot just by standing over them and acting as a human bookmark to help them remember their temporary files that they're creating. It's a great way to start. So let's try it now. Ah, there we go. Now it worked. So now let's see if our make, if I leave the default, CC, GCC OR lab. Oh, yeah, typos. I'm forgetting a bunch of 5s. You guys should have caught that. There, now we have all the 5s in the right place. Now if I say make all, it shows you what it did. And now I can run it. Args 5, 5, 7. It gives me 12. Aha. But where's my foo? I don't have my foo. I need to put my foo in there. Okay. So where would you put foo? Now, how does this work? Well, when I say make all, it calls this, which indeed calls this, which indeed calls this, which then down calls this, which calls the C source code, and then we're done. See how that works? All calls this, that. It works its way down that way. Okay. And my Raspberry Pi is still grinding away over here. Oh, it's all done. Okay. Give you an idea of this is what the makefile looks like for compiling Python. As you can see, it gives you a lot of flexibility in your compile that I teach you nothing about. Did you know that you could use make to create your very own static website generator? You can use make to do all kinds of crazy things. There's another tool in this category that I want to mention. It's called ANTLR. You will probably never see this in school, even in a master's program, or even in a software engineering program. What is this? It converts source code from one language to another. So you can take C++ code and convert it to Java, and Java into something else, Kotlin into something else. It works at the source code level. It's a bear to learn how to use.
Does it also translate over different versions of the same programming language?
I believe it will let you go from old school C89 into the modern. Taking modern and going back, I think it would work too. So it says reverse, but take a look at it. The guy that's been developing it has been working on it for 30 years. Talk about knowing how to do tokenization of programming languages and writing compilers. That's where you'll learn it. Okay. If I was knowing what I know now, if I had to go back into computer science and take the compiler class, I'd use Antler. Hint, hint, future for you. You're gonna have to write a compiler. Use Antler. All right, now let's see if we can get this to work. I have to go back and edit my args and put my foo stuff back in. Now let's do make all. If I don't, I can type in make all, but that's the default. So if I just say make and hit enter, what did it do? Well, it compiled my object code first, and then it basically converted my object code into my executable. So now I should be able to run it again and get an additional answer of +8. Yippee skippy, my make file works. This is also part of the assignment, your make file, because we will be doing the following. We will have something called fib for Fibonacci. We'll have something called fact or factorial. And we'll have something probably called, let's see, we're working with integers. We could probably go with POW for power. I might have to change, we'll use that. Because I think POW is a reserved word. I want to make sure we don't trounce it. Whoops, those are .O's. This is where we're going. This is your homework. These are the pieces of code that we are going to convert from standalone C into its header and include. And you're going to use the make file to link it all together. This is not technically assembler, but this is very technically real world. Okay. This is it. Okay. I have found that teaching the pragmatic side of things is more beneficial for students than all the lovely esoteric things. So let me write those names down to make sure I keep them the same. Fib, fact, and POWR. Now, back to our little friend here, Raspberry. It finished compiling. I compiled as a single user. I happen to be the admin user on the Raspberry Pi. Let's do this. Python -v. Whoops. 3. What version of Python do I have? That's the base install that came with the Raspberry Pi. 3.10. What did I just compile for? 3.11. Now, if I install this, am I going to have a headache? Yes. How do you solve that headache? It's called virtual environments. Go does this, Rust does this. Your modern programming languages do this. Okay. I will demo on another machine to show you what it does. Okay. Let me close this. Well, I'll just leave that up. Go here. What? No, that's pretty modern. Let's see. .311. Okay, perfect. They're different. Yay. All right. Let me see if I got it here too. Python. Yeah, this is more real. This might work better. Hold on. Whoops. Fat finger day. Python 3-B 310 VP1Y. It's the same thing. I could do that. Let's not do that. You know what? I'll just install it on the Raspberry Pi. It's not going to break anything. SUDO, make, install. Notice now I'm running SUDO with make. It's taking my source code, my object that makes Python 3.1.1 part of my system. Oh, look, what did it do? If you're not careful, you can really screw up your machine, which is fine. All you have to do is reinstall, rebuild, just fine for your home computer. Okay. Now, what has happened? That's my new version of Python. Python 3, just change directory, do that again. It sees it 3.10. Let's see. All right. These next few steps, you'll probably never need, but as if you're a Pythonista, knowing how to manage virtual environments is job one if you're going to program in Python. Because when you install Python on your computer, it's in all your system directories. When we're running the Jupyter Notebook, that's not the system version of Python. That's another version. So we create a virtual programming environment, and it's very simple. Notice where this is. Python 3.11 is in user local bin, isn't it? Here's how I do it. Let's see if I have a directory here. Let me go to my exit. Make sure I got it installed right. Oh, I didn't install it on the Raspberry. I was installing on the Jeremy box. Oh well, it's already installed there anyway. I'll do it on this one. Now that we're all confused, I'm now on this machine. I say which Python 3. Anyway, what does this have to do with all this stuff? It's all part of the make file. So that's where it is. And now if I run it, it's 3.10. Okay. Let's look at user local bin and see what I have in there. Oh, look, I got Python 3.12 in there. I want to use Python 3.12 for my static website generator, or my Jupyter Notebook, or my Conda install, or my pandas, or whatever. So what I do is this. I find an empty directory somewhere, and I will call it like this. I say user local bin Python 3.12 -en no, V virtual environment. And then I give it a fully qualified path name. And I'm simply going to call it home DKP, and I'll call this static, as in my static website generator. And I hit enter. Except I did it wrong. User local then. Oh, 312, right. 312. What am I missing? Something's obviously missing. Virtual environment. Oh, dash M. Yeah, that's it. Permission denied on DM ticket static. Oh, yeah. Used to be Tux. Magic. What just happened? LR. I created a new directory called static. And in this directory is called static. I now do this. Source. Then activate. My prompt has changed. What version of Python do you think I have now? Just take a guess. The new one, 312. And I don't need the 3. 312. Now I have a completely separate environment. So I can now do pip install makedocs and install makedocs for this version of Python that will not screw up the system. See how easy that was? Everything's easy when you know what you're doing.
You said make docs.
Pardon?
Make docs.
What is it?
What was the command?
The command?
The one that you just put in.
Oh, what I just did? Oh, to make it?
Yeah.
Oh, to install it.
No, just the one that you just put in right now to make it.
How to make the static website.
No, I saw that. The one you just put in right now.
Okay. Oh, the command I just did.
Yeah.
I did pip install make docs. And then it's telling me, hey, you need to run pip install upgrade pip. Pip stands for the Python package manager. Okay, that's cool. There's one package I like to install. It's called pip review. It's actually really pretty cool. You can run pip review once you have it activated, and you just hit enter, and it tells you if it's up to date or not. So you can keep all your libraries secure. I do this on the Jupyter Notebook, our thing all the time. What I'm giving you is real sysadmin stuff here. Is this pip review? I now have a separate working arena to install and make a playground for just this machine, and it won't mess up the production instance of Python. Python virtual environment, okay? And the command, after I compiled Python, I did the, to get out of it, you just type in deactivate and watch what happens to my prompt. My prompt goes away. If I type in Python again, it says, not there. I have to use Python 3. So there it is. Notice this is 3.10. That's not the one I want. I do exit. Now, you can have multiple of these on your computer. Okay. I bring this up because this is becoming the way of programming. Go and Rust support this idea. You may be working on legacy Go code that only works with 1.1, but you want to use 1.7. Well, how do you do it? You do this virtual arena thing. Okay. So this is very practical stuff. May not be practical in your immediate future, but now you know. So if I want to do make docs, and I'll show you that later. That'll do that for the Linux class. Okay. Back to a make file. All that just to show you this. Now I get to show you some code to get you started here. Let's do this is help I spell. All right, folks. Here's a Fibonacci sequence. Convert it to a function and put it in your args lab 5. We'll also do this for Fibonacci or factorial and power. Okay. First of all, let's look at this code and see what it does. Okay. So if I want to compile it just real quick, just to see what it does, if I type in GCC and hit enter, what happens? What's the executable called? That should be committed to memory. A.out. It's the same thing for G++. If you just hit enter, I get A.out. That you should have memorized because that's a really good Yeah, you want to be a programmer? Yeah, when you take GCC with no flags, what's the output file? And if you said, they're going to know you don't know this. You don't know the command line. A.out is the default. And every time you run GCC by itself like that, it trashes what's in A.out. So don't put anything important in A.out. And I just say A.out and hit enter. 34. There's no arguments in there. So this Fibonacci doesn't do anything. It just takes what's there. Oops, I want to edit it. Now, your question is, we have arg1 and arg2, right? When we say args lab 5, 7, 3, it adds those two values together. So where would we put the 7 and where would we put the 3? You have to figure out the code to find out where you want to put your arguments. It's all right, we're going to do this more than once. Nobody should start with power. That might be a little easier. Do that. Let me go over here. Leave that up. I know you're in there. Oh. Give me a second to find my homework. Factorial. Let's walk through this process. We know what foo does, right? We're pretty comfortable with that. Let me remove those. Add this one. So we'll do power in class to give you a heads up. Do these files exist? No. We need to create them. So let's do that. How do I convert this into power? All you math people. Yeah, just multiply it by itself. I can still call it X. Return X times what? X. That's the same thing as power, right? For what we're doing. Make sense? No? Yes? Fuzzy? X times X is what? That's the same as X squared, or X to the second power. That's all we want to do here. I want to make it simple. And do the same thing. What did I do? I copied foo.h to power.h, copied foo.c to power.c, renamed everything from foo to power, and changed the formula to X times X. That's it. Now that we have our make file made, how much work does this take? Virtually nothing. Make nothing to be done for all. That means I left something out. Power, power, power. Oh, I should do make clean first. Ooh. Notice make clean. You see the lovely typo? Remove power.c. Oops. That removes the source code. Oh no, I don't want to do that. I want O as an Oscar. All right. So now let's do make, clean, remove all the .o files. And it's telling me I can't remove power O because it's not there, which is fine. So now let's do make. Oh, look, compiled it all. Hit up arrow to run it again. Somewhere in here. Oh, there it is. Oh, nuts. It compiled, but it didn't show me power. Why? I didn't call it. Right here. And I'll use A. So by the end of this exercise, you should be pretty comfortable with creating headers, creating a make file, modifying things, and testing it. You can make for all sorts of things. Make, typo. Let's see here. Implicit function power. POWR, POWR. Let's 2727 in argc. So go down to line 27, column 27. Yeah.
Don't you need to include your power at the top of the header file?
Duh. Yeah, you are correct. What'd I forget? Yeah, I need the include. Oops. Now let's do make clean. Now let's do make all. Now let's run it. Haha! We're cooking with gas, as they say. Which is now, you can't buy gas stoves anymore. I find that amusing. Anyway, time to update our euphemisms. Cooking with microwaves. Cooking with our air fryer. All right. So what have we done tonight? Well, let's do a listing here. We continued from last week here. Last week, we started with argv and argc. Last week, we put in a check to make sure we had two arguments to our command line, so it wouldn't do what? Core dump, seg fault. Okay, put that little if statement in there. And we left it at the point where we were going to add foo C and foo H. That's where we left last week. This week, we picked up where foo C and foo.h, we keyed it in, we got it to work, then we added a make file with a nice, lovely side jaunt into Python virtual environment. Trust me. Wow, now if you read up on a virtual environment, you know what it will do. Trying to learn it from scratch, tough. Ask me how I know. And we created a make file. And the make file, we learned something really important. Tabs. Make files need tabs. Okay. And then we created our power C and power H by doing what? Copying foo and then changing the formula. That's what we've done. Okay. The lab 5, we will add 2 more here, factorial and Fibonacci. Okay. And that will be in the lab. I will post those. And let me see if I can find that code. Might be helpful, huh? Code from memory, your own Fibonacci sequence. Yeah, most people wouldn't know that. Let's see here. Okay. Here's a standalone factorial. So this is the code that you will want to compile and run, tinker with on both machines. Notice there's this thing called save temps. What does that do? It's saves all your temp files. There's a bunch of them. And they have information in there. Okay. And what's this one do? That tells us what level of code we're using. We're forcing it to a standard. I think it defaults to C11 anyway, but that's my point. Okay. So when we pass our value here we want to pass X in there because we kind of need to start at 1, and we pass our total A to base equals 6 and let it do its thing. We might just get some problems if we get really big numbers. Then what do we do to fix it? How big is an integer? Yeah, we go to a word or a double word. Expand it. Okay. All right. And let's see here. I want to copy. Let's just do the cap to 24. And we'll call it fact.c. Modify to use with lab 5. Make file. Okay, put in a comment right here. This needs okay, i.e. A is what we've been calling it. The A arg. Okay. All right. That's the Fibonacci. Excuse me, factorial. Let's compile this and see what it looks like. I'm going to steal that. Look at all those fun things it saved. I got a C, a .I, a .S, and a .O. What are they? What do they do? What do they mean? That's part of the homework too. Okay, go find out. Now, if I run it, 720. Let's edit this briefly and change a init base to how about 60? Any bets? Oh no, zero is not the right answer. Well, integer can only get to 65,535, I guess. It's bigger than that. So it says, sorry, I quit. How do we fix it? Well, lots of ways to fix it. Here's one way. Let's do double. I think that's right. Am I getting my C++ mixed up with the double word or double? Yeah, let's see if this behaves. I might have to look it up. I don't remember. Yep, double isn't right. Big word. Long. That's what it is. Long. We'll try long. CWLONG. Ugh, darn it. That's how you can tell you're following a VI programmer. There's colon WQs all over the place. Still zero. So maybe that number is just too big. Let's go with something like 12. Oops, I got to recompile. Yeah, that's bigger than 65,000. And it's only 12. So if we pass a value from A, which is our two digits summed, if we say 100, 100, 200, and we pass it to this, we're going to have a problem. Okay. So we'll have to see how big our numbers can get on a 64-bit. And this will be somewhat different on the Raspberry Pi. Not significant, but somewhat. You can see where we're going. Okay. How do you take that code and make it something like, whoops. What do you mean? Oh. That. So what do we need to do to convert our fact.c into a fact.h and a fact.c? I'll leave that as an exercise to the reader because that's part of what the homework's about. So I will add that in there. Okay. So for our lab 5, we're going to add Fibonacci and factorial. I've already done power for you, the make file, and then big ints. How do we get around that? On that note, I'll stop.
Your make file one more time.
Oh, yeah.
Thank you.
There is the factorial. Let's see if I can find the Fibonacci. And here's a Fibonacci. So the Fibonacci will be need to be renamed to fib.ce. Now this one's a little trippy because if you look at the code, it's like 2 characters off from a bubble sort. So it's really similar to a bubble sort, but not quite. So we take our value of A, put it into T, B is into A, and then we take acute, this plus equals means add it, take what's in T and add it to B. And these are all integers, so we may want to expand the sizes so they won't die on us. Oops. Whoops. Why does it do that?
Yeah.
Oh, there's no main. My bad. Let me fix the Fibonacci here. Oops. How should we make this go? And that team. Let's go with decrementing one. Let's go with it would help if there was a print in there. Ah, there we go. Working Fibonacci. And a working factorial. I'll put these in the homework. So. Pardon?
Can I see how you structure your make file?
Oh, make fun.
Yeah. Sorry. I'll talk.
That is,
I wrote it down, but I think I got something from it.
where did I put it?
One is on the RAS.
Where was that? Generate box.
I want to say it was on the RAS. I don't know if
Oh, wait, so
Like, is that-
Oh, demo. See if that's where I put it. Nope, that's a different one.
yeah, that's your Python.
We did it.
We did.
Where did I put it? Isn't this fun? It just disappeared.
I mean, I know I have it on. I have a picture there, but it doesn't. That's where I think it is.
Oops. Did it? And just remember tabs.
Yes, I ran into it earlier, and then you said it, and I was like, oh, that makes sense. Awesome.
There you go.
And then I had a couple questions. Do you guys still do the computer? Is there an actual computer club here?
It meets on Tuesdays at 5 o'clock. And as soon as my SSDs come in, we're gonna be putting SSDs in all the servers.
Awesome.
Well, half of them.
How do you sign up for that?
Yeah, yeah. You want to sign up for it?
How do you do it?
Let me go get the sign-in sheet and then I'll add you to the email list. And as soon as the parks come in, we'll be doing. Here's my precision upkeep on these. This is for the servers. If you're interested in working on a server, we know. Put your name on the list. Yeah, generally I'm here. I'm generally here by 1. But it may have to whack on the wall. But if you see through the window, that door is open, like, good bet. If I'm not here, wait 5 minutes.
No.
I mean,
Put anything in for Fibonacci or
they're running around.
I didn't see one.
The administrivia.
There's no inputs, right? Yeah, I don't think so. I think it's just.
Yeah, where I left it this week is the Linode server. Will show you. Wait, should I?
Wait. Yeah, oh, yeah. Okay. I'm so close.
Yeah, I'm like right there to the Fibonacci, I just don't know. what's wrong with this part. Yeah.
When he just went silent or type of way, like,
So that when he's talking about the type.
oh, yeah.
He lost me.
That was so soft. You can see.
Hey, professor.
That's funny.
Oh, yeah. I guess I should turn off.
It's just give me thumbs.
Yeah, I guess I should turn off Zoom, huh? Okay, I'm stopping sharing, stopping the video. Thanks. See you later.